This lecture covers actuators for haptic devices. An actuator is anything that allows you to generate a motion or force input that the user can feel. And in our case, that actuator is typically a motor. So here's an interesting diagram that covers a bunch of different actuation types and some of the advantages and disadvantages of them. What it does is it plots the general weight of an actuator versus the power to weight ratio. And ideally, you would like the weight to be very, very low and the power to weight ratio to be very, very high. And you want the weight low, not because you'll necessarily be picking up your haptic device, but because you will feel the inertia of parts of that actuator as you move around the end effector or the haptic interaction point. So we'd like to be in this area of this plot. But unfortunately, the only thing that's up there is shape memory metals, or shape memory alloys, as you might have heard them called before. While they look wonderful because they sit in this perfect corner of the plot, they have other issues like very slow response time. And so while some people have tried to use shape memory metals in haptic devices, it's not at all common and still an open area of research. So unfortunately, shape memory metals are out for us. Pneumatic actuators are another possibility. They have some intermediate advantages. Pneumatic actuators simply use air pressure in order to create a force on the user. Problems with pneumatic actuators can include actually being able to translate that air pressure into a very precise control output that the user can feel. And so we're also going to eliminate pneumatic actuators here. Finally, there's hydraulic actuators, which are similar to pneumatic, only they're using water instead of air. And they just tend to be much larger and heavier and potentially messier as well. So these get eliminated. So what are we left with? We're left with direct current motors, which are not at all at the ideal spot on this plot, but at this point, it's the best that we can do with relatively inexpensive actuation technology. So for kinesthetic haptic devices, this actuator of choice then is the electrical motor. It's a DC or direct current motor as opposed to an AC or alternating current motor. They're brushed, and we'll see what that means in a minute, and they have permanent magnets. So a DC permanent magnet brushed motor. So what does such a motor look like inside? And this is not a picture of the same motor you have in your hap kit, but it has basically the same components. So the way that it works is that there's an armature which is inside, and I'll switch to blue so you can see this. So this is the armature here, which rotates inside the motor. And then this is the housing, which is stationary. And on that stationary housing is the permanent magnets. And in fact, you can see the permanent magnets here and here on this picture. And the idea is that current that goes through these coils will generate a force relative to these permanent magnets that's going to cause the rotating armature to spin. So how do you actually get current onto this spinning thing? Well, that current is transmitted through brushes. And in this diagram, you can also see the brushes. I'm going to get rid of those so I can circle new things. So here's a brush, and here's another brush. And the brushes are actually making contact, physical frictional contact, through to the armature, which is rotating. And these contacts are constantly switched, and that way the armature magnetic field remains fixed. And it's switched, as you can see. These components on the armature have contacts and then areas where there's no contact. And as you make and break contact, you are continually switching between different coils of wire on the armature so that you're getting the right set of forces in order to keep rotating the motor. This might be a little clearer if we look at the next diagram, which is as follows. So this just looks at a single conductor in all those coils that were shown in the motor picture on the last slide. In this case, we say we have a permanent magnet with north and south pole, and it's creating a magnetic field, which is going like this. And there's a single conductive wire, which is going through that magnetic field. And when there is a current, which is flowing through this conductive wire, and it's inside of a magnetic field, that's going to generate a torque. So a torque, tau, will be generated on this conductor. When that torque is generated, that will cause the armature to spin, and when it spins, you go into a new set of segments. So maybe instead of being on a conductor, you're now on an insulator. And so when the conductor is in a place where it shouldn't be, it can't get torque from the permanent magnets, it's not trying to get current flowing through it. There's actually going to be an insulator contacted down here. And instead, there will be some other conductor at that point which will be active, and that one will then have a torque applied to it. And so this is the basic circuit for a single conductor for a DC motor. Some important DC motor terms that you're going to come across when you think about haptic design are as follows. One is the cogging or torque ripple, and we'll see this more in another slide. And that's the tendency for the torque output to ripple as the brushes transfer power. Because the brushes are switching between conductors and insulators back and forth, the torque output isn't perfectly going to be constant. And so we'll see what that looks like in a minute. Also, you would like the motor to have minimal friction and damping. There can be friction and damping in a device because of the bearings in the motor that support the rotating armature, because of the brushes that physically contact the electrical circuit to the rotating armature, and also something called eddy currents, which are small currents which start to build up in the armature, and they effectively damp out some of the power of the circuit. And then there's also a very important parameter which isn't often quoted or necessary for a lot of motor applications, but it's super important in haptics, and that is stall torque, because that's the maximum torque delivered by the motor when it's operating continuously without cooling. And since when you're holding onto a haptic device, the motor's not really spinning typically much at all, you're really just feeling the torque that's output by the motor, it's important that this max torque be as high as possible. So the stall torque you would like to be high as possible. And these things, cogging and torque ripple and friction and damping, you would like to be low. So these are what you desire for your haptic device. And that's because when you're trying to create a haptic virtual environment, you don't want the user to feel the mechanical properties of the motor. You just want them to feel the forces that you're rendering. And that stall torque is going to limit how much force you can render. So this slide shows this torque ripple I mentioned in a little bit more detail. The idea being that each one of these bands here, represented for a Maxon motor, which is the kind of motor that we're using in our HAP kit. Each one of these lines represents the torque that's generated by one of the conductors. And if you have lots of conductors, the idea is that the torque that you get on the output is a kind of ripple that rides on top of all of these different conductors and switches as it switches between them. And so depending on how many conductors you have, or you could also say commutator segments, there's also the number of commutation points, that is, connections that you have between the brushes and the motor, you can get different amounts of torque ripple. So if you would like to have very low torque ripple, of course, you're going to have the maximum number of conductors and commutation points and segments as possible. And then your percentage of torque ripple in terms of your overall torque is going to be very, very small. But of course, that adds cost. And so we try to get the lowest price motor that we can for a haptic device that has low enough torque ripple that the user can't really notice it. Unfortunately, most motors have a lot of torque ripple, and motors that are good enough for haptics so that users can't notice and feel that torque ripple, they're pretty expensive, as we'll see in a little bit.